present many derivations. I can just discuss the ideas and the results and tell you what you should try to do on your own. These are small but useful exercises. So, the first thing I will deal with today is the case of a non-relativistic particle with a given mass and a given electric charge moving in an external electromagnetic field. And you know, since I assume that the particle is non-relativistic, this is the left hand side of the equation of motion, and on the right hand side is the force acting on the particle at the point x at time t. E is the electric field and B is the magnetic field, and these are given. Now, it turns out that this equation as it stands cannot be derived from any Lagrangian. Probably many of you know it, and I will leave it as an interesting challenge to you to convince yourself that you cannot derive it in this form from any Lagrangian. So, to get a Lagrangian description, it turns out that we must write the electric and magnetic fields in terms of a scalar potential and a vector potential. A is the vector potential and phi is the scalar potential. I am using the units that I was born with. What is it called, ESU or something, right? It is very hard to change even in midlife. In later life it is even harder to change. So, it turns out that only if you write the electric and magnetic field in terms of potentials in this way and put these expressions into the equation of motion, then that equation of motion can be derived from a Lagrangian. And the steps are not complicated. So, I will just write the expression for the Lagrangian. In this problem, the Cartesian coordinate vector coordinate x is the generalized coordinate, x dot is the generalized velocity, and it is a fairly simple manipulation to see that there is a Lagrangian which can be constructed, and this is what gives as the Lagrangian equation of motion for this Lagrangian. You will get this original Newtonian equation of motion in terms of the electric and magnetic fields. There is one interesting thing that one must check. I will leave that to you. Given electric and magnetic fields, the potentials are not unique. This everybody knows. And if you were to define a new vector potential A prime by adding a gradient of any function chi, real chi, to A, and if you define a new scalar potential to accompany this change in the vector potential. So, you go from A and phi to A prime and phi prime in this way for any choice of this quantity chi. This is called a gauge transformation in an electromagnetic theory. You will see that the electric field and the magnetic field do not change. So, the question is, what if I use A prime and phi prime instead of A and phi in constructing the Lagrangian? Obviously, it is not going to affect the equation of motion because they involve only E and B. You please do a simple calculation to find out in what way does this Lagrangian change if you replace a prime and phi by phi prime? How does the Lagrangian change? And even though the Lagrangian changes, why is it that the corresponding equation of motion does not change? So, these are very elementary exercises. I will leave them to you to work through. They are discussed in these notes. So, you can try first on your own and then go to the notes if necessary. Okay. Now, I come to the important concept of the Hamilton principle. As I mentioned yesterday, there were attempts during the 18th century to write down some kind of variational principles to derive the Newtonian equations of mechanics. And many people took part in this kind of work, but the form in which the action, a principle of that type has been written, has been constructed by Hamilton, is the most useful one and is the one we still remember. We have forgotten all the earlier ones. All right. Now, I also mentioned yesterday that the Lagrangian equations of motion, which we described in detail yesterday, they have a covariance property. What does it mean? It means that if you take a set of generalized coordinates q and replace them by other generalized coordinates in such a way that this transition has an inverse, etc., and differentiable, etc., the form of the Lagrangian equations of motion is maintained. Lagrangian itself as a function may change in its form, but the structure of the equations of motion is preserved by any invertible change of generalized coordinates. This is called the covariance of the Lagrangian equations of motion. Such changes of coordinates have also a name. They are called point transformations. I may come to this a little later in little detail. So, now Hamilton's principle is a way of expressing the equations of motion in which this covariance, this fact that Lagrange's equations do not care what generalized coordinates you use, becomes obvious. Okay. That is one of the great merits of the Hamilton principle. The other part is the following. The Lagrangian, Newtonian and Lagrangian equations of motion, as we know, are differential equations. They tell you, if you know the condition of a mechanical system at a certain time, what happens to the state a little time later. So, it is a description by differential calculus. The Hamilton principle and other precursors to it try to describe the motion not over small intervals of time, but directly over finite intervals of time. The basic idea is the following. Supposing you are given a time t1 and you know the variables of the system at that time, and then you say, I do not want to give differential equations of motion. I choose a time t2 later, finitely away from t1, not infinitesimal, and then I give some information here. So, I give partial information at an initial time, partial information at a later time, and then ask, given this much information, can we work out the actual motion of the mechanical system in going from T1 to T2. This would be called an integral principle and global approach, global in time, to the equations of motion. So, Hamilton's principle is of this kind. From the differential point of view, Newtonian or Lagrangian point of view, the information needed to determine later motion, as Shamik described yesterday, is to give at an initial time all the coordinates and all the velocities. If they were all known and if the equations could be solved, you would know the future. In this integral approach, we do not give complete information at the time t1. We give some information at t1, balance information at t2, and then ask how does the system move to connect these two given pieces of information. So, there is a configuration space. I am sorry, my handwriting is degenerating, it is not a recent phenomenon. The configuration space is formally denoted by capital Q. It is a set of all possible configurations of the system at a given time. It is a collection of all points described by any given system of generalized coordinates. So, then you say, you approach the problem in the following way. In the configuration space, at an initial time t1, suppose the generalized coordinates or the configuration is specified. Okay, I do not put the index superscript r for many degrees of freedom, you can assume it is there. And then at a later time t2, you give the values of the generalized variables coordinates q of t2. Then, so I should draw a diagram, I will in a moment. Imagine drawing a curve capital C in the configuration space connecting q at t1 to q at t2. So, what is C? C can be written as a choice of values for the coordinates at every time from t1 to t2. So, this is a curve in Q, and we say the initial and final configurations are given. All right. Now, I can rub this out and draw a picture for you. Picture is like this. Not bad. This is a picture of configuration space. Here is the configuration at time t1. Here is a configuration at time t2. And you imagine connecting them in by a moving point in time, going from q of t1 at time t1 to q of t2 at time t2. So, the problem is the following. Instead of describing the motion of the system by differential equations, we ask the question in this way. Is there a principle which will allow you to say, out of all the paths C that you can imagine, which one is it that is actually picked out by the equations of motion? Which path does the system, mechanical system, follow if you say, I want it to start at this point and I want it to end there? With that much information, is there a principle which tells you how to pick out the actual path? Okay. So, this is the spirit behind Hamilton's principle. What we do is, given any C, we define something called the action for that path. It is called a functional, not a function, because it is something which depends on an entire curve. Okay. So, action for the trajectory C, and it is defined as the integral t1 to t2 dt L q of t q dot of t. For simplicity, I will assume there is no explicit time dependence in the Lagrangian, just for simplicity. So, this is an integral over time from t1 to t2, and it starts at q of t1, ends at q of t2. So, this is called a functional action functional. Why is it called a functional? Normally, we have functions we deal with which have as arguments a finite number of independent variables, normally electric field, magnetic field, Lagrangian itself, and so on. Here, the argument of the action is not a finite number of independent variables. It is the values of q of t for every t from t1 to t2. It's an infinite number of arguments, independent arguments. So, the word used is functional. Now, imagine you change C to a nearby C prime. That is, at each intermediate time, you make small changes in the coordinates q at that time. All right. And so I will describe the new path, the C I have defined there. Maybe it is good to write C prime right next to C here. At each time from t1 to t2, I make a small change delta q of t in q of t at that time to get the q prime of t, with the condition or the agreement that at the initial and final points nothing changes. All right. This delta q, the change from C to C prime, it starts at 0, that is, the initial point is unaffected, and it ends at 0, but in between it is allowed to vary a little bit from C. Then it is a matter of interesting and nice calculation to ask, to find out by how much has the action changed. Phi for the path or trajectory C prime minus phi for the original C, to first order in these small quantities delta q, and with the condition that the end points do not change. Then this is a calculation. I will not go through the steps. It is something which can be done quite easily. I leave it as an exercise. Sorry. Now, I will put in the various degrees of freedom. This is an easy calculation. I do not wish to spend time doing it. I leave it as an exercise for those who have not done it before. In getting this expression for the change in the action, in this situation, we have to use this condition that the end points are not altered. Now, you look at this expression. What appears in the integrand multiplying the changes delta q r in each of the generalized coordinates is just the expression which Lagrange's equations of motion say should be 0 along the actual motion. All right. So, now we can state the Hamilton action principle in this way. I will say it in words, I will not write it, but I will say it very slowly. Given any initial configuration at time t1 and final configuration at time t2, the actual path that the system follows from time t1 to t2 is such that if you make small changes in it in intermediate times, the action does not change. I repeat, given initial and final configurations, the actual path chosen by the differential equations of motion or the actual path followed by your mechanical system is such that if you imagine small changes about the actual path, of course, the endpoints being untouched, action does not change, because this expression is 0 according to the differential equations of motion. So, if this was the way it was formulated by Hamilton around 1835, and yesterday Shamik told me that there are sometimes these days people are taught Hamilton's principle is the starting point to getting equations of motion. So, one should not have this misconception, right. The equations of motion were first written, as I said yesterday, by Newton in a notation which is never again used. Newton gave the equations of motion in his own notation. It was rewritten by Euler and others in the next century by the notations introduced by Leibniz and then developed by Lagrange. So, the approach to the description of motion was by differential equation system. And then there were efforts in the 1700s by Maupertuis to say there is a global way of describing the motion of physical mechanical systems, but his formulation of his what is called his principle of least action was not very precise, and his derivation was, Sommerfeld says, even worse. You must see exactly how Sommerfeld describes Maupertuis' work. Then Euler and Lagrange tried to improve the statement and proof of the Maupertuis principle, but it was still a little bit ungainly, I can say. And finally, in 1835, Hamilton expressed it in this way, and this is from then onwards the standard accepted way to state the principle of least action. Okay. If the Lagrangian is of the usual non-relativistic form, and I told you yesterday much of all this development, formal development in classical mechanics took place against the background of non-relativistic physics. So, if the Lagrangian has a usual non-relativistic form, a kinetic energy which is quadratic in q dots and a potential energy which is q dot independent, you will immediately see that the equations of motion coming in this way will be second order ordinary differential equations. Now, I want to describe an extension of the Hamilton's principle in which we do the following. How to show it in a diagram? Yeah. Huh? Yeah, we specify. No, because the equations of motion are typically second order differential equations. So, from the differential equation point of view, how much information should be given at T1 to determine the motion? Q and Q dot. But in this approach, you do not give Q dot, you give only Q at T1 and also you give only Q at T2. So, except for some exceptional cases, in general, given half the information at T1 and half the information at T2, no Q dot is specified. Only Q here and Q there is specified. In general, except for unusual circumstances, there will be a unique path from here to there for which the action is stationary. Stationary means no change under small changes in the path. Okay. So, this is Hamilton's principle. Okay. Now, there is an extended form of Hamilton's principle which is very interesting and which is most often not taught at least in our institutions, I think. This is a principle in which we allow changes in the endpoints. And now I want to modify this diagram. I start with time t1 and q at t1. I end with t2 and q at t2. Now, in what way shall I vary the path? In the derivation up to now, I said the endpoints are untouched. Now, what we will do is, when we draw a nearby path, we will imagine that it starts at a nearby point to q of t1 at a nearby time. We allow the initial time to vary by a small amount, and at that altered initial time, we allow the q also to vary from q of t1 by a small amount. And we say we will allow it to end here at a slightly altered final time. So, what are the changes we are imagining? We are imagining a change in the initial time t1. We will allow t1 to change to t1 plus delta t1. We allow the final time to change t2 plus delta t2. And in between, we allow q to change at each intermediate time in the way we have done it here. So, this is the more general variation of the path which we consider. And then we ask the question, what is the expression for the change in the action under this kind of change in the path which we are specifying? So, I hope you understand that how it differs from the previous calculation. So, I will now write down the expression for delta phi, then tell you a little bit about it. First, the definition. Now, I write that change as capital delta, not little delta, just to indicate that this is an expression corresponding to this wider class of variations of path. So, initial point, initial time, final time are allowed to change. Initial configuration coordinates, final generalized coordinates are also allowed to change. So, it is not starting from the same initial point and ending at the same final point. So, what does this mean? This is, of course, it is the difference in phi. Now, I will use the letter c prime, except that c prime runs from a different initial time to a different final time, etc. So, what will this be? This will be, I first write it so that the ideas are clear. All right. So, this is the expression, this is the definition of the change in the action in this situation. And now, I make the following notation. At any intermediate time, let us say this is at time t, this here is q of t, this is q prime of t. And the difference between q prime and q will be described exactly as before. So, leaving aside the endpoint contributions, I will still use this way of describing the changes made in the path along the interior of it, you can say. So, now the question is how to calculate it. How to calculate it, I leave it to you to calculate. And I will give the expression and describe it, describe its properties. It turns out, first there is a contribution exactly like before, which must be there, of course. this contribution has to be there, because the earlier discussion is a subset of the present discussion, but there will now be more terms. And what are those more terms? I will just write them down and then describe the situation. Earlier, for the simpler variations where initial and final times and points were not altered, the change in the action was an integral with respect to time. Now what happens with this extended Hamilton principle is that you have this term as before, and then you have what are called endpoint contributions. There is a piece coming from the initial point of the curve, there is a piece coming from the end final point of the curve. Those things involve delta T1 and delta T2, the amounts by which you are allowing the initial and final times to change. So, this last term on the right with the minus sign is this contribution proportional to this delta T1 and this delta T2. Then the penultimate term, it is something proportional to differences in the Q's between the new starting point and the old starting point. So, I do not know how to, I do not want to complicate this too much, this diagram, but I will just indicate capital delta of Q at the initial time is the new coordinate at the new initial time minus the old coordinate at the old initial time. So, this is not this delta Q, this is the change in each coordinate at the same time. But what I am talking of now, delta, capital delta of Q is different, it measures this difference, new initial coordinate minus old initial coordinate, and see the time arguments are different here. And similarly, this will be delta Q of T2. So, now it turns out the calculation shows the change in the action has this form where I have to describe what these new things are. Well, I just write them down. The coefficient of the changes in the initial and final times delta T1 and delta T2 is this expression constructed out of the Lagrangian, and this in mathematics is called, what is it called? Anybody tell me? I mean younger people. Huh? No, I have not yet used that word, but what is this called in terms of the original Lagrangian? Before, purely in mathematical, exactly. This EL is the Legendre transform of the Lagrangian, and in this expression it is to be thought of as a function of what? Q and Q dot, because L is a function of Q and Q dot, the first term is only Q and Q dot. So, this is the Legendre transform of the Lagrangian viewed as a function of Q and Q dot. That is what comes in the term proportional to the changes in the time instants, initial and final times. And this thing is called, well, I jumped the gun, it is called the canonical momentum. PR is the momentum, canonical momentum corresponding to the coordinate QR. And here is its expression, it is to be thought of at this moment as a function of Q and Q dot, obviously, because L is a function of Q and Q dot. Okay. So, the extended Hamilton principle is to be stated in these words. Under small changes of the path C from initial time to final time, allowing for changes at the endpoints, you allow delta t1 non-zero, allow delta t2 non-zero, you allow q prime at the initial time to differ from old q at the old initial time. So, the endpoints are not held fixed in configuration space. The principle says the equations of motion are obtained from the statement, the change in the action functional shall consist only of endpoint terms. This is a very careful statement. Earlier statement was for restricted changes in the path, the action shall be stationary under small changes around the actual path. That was the statement. Delta phi shall be 0. Now, in the extended action principle, the wording is different. You are imagining a wider class of variations of the path. You are allowing endpoint changes. Then Newton and Lagrangian equations of motion are contained in this declaration. They are such that under small changes of the extended type, the action changes by endpoint terms alone. This is a statement, a declaration. All right. If you accept that, it means that this fellow must be 0. Now, this is the ordinary differential equation of motion, but there is some extra value here. You go on to complete the action, the Hamilton principle, by saying in the endpoint terms, there is a piece proportional to delta t which we shall call the Hamiltonian. It is the Legendre transform of the Lagrangian. And in that boundary term or endpoint term, there shall be terms proportional to changes delta capital delta q. They shall be called the canonical momentum variables conjugate to the coordinate variables. So, what is it that has been achieved by stating it in this extended manner? It gives you 3 things. The traditional differential equations of motion, Newtonian, Lagrangian equations of motion, definition of canonical momentum, definition of Hamiltonian. All of these come out from this action, this version of the action principle. I hope you like it. This it is not often discussed even in mechanics books. I don't know if in Goldstein it is given in full detail. The person who, well, let me put it this way, I learnt it from my teacher Sudarshan. Landau, it will be there. Yeah, of course it has to be there. And I see. Okay, that I am not familiar. Beg your pardon?
Non-contemporaneous variation.
Okay. Yeah, exactly. So he, Sudarshan had told me he had appreciated it and sort of learnt it deeply from Schwinger. And Schwinger's action principle is a version of this Hamilton's extended principle in the context of quantum mechanics, and it was very powerful formulation in Schwinger's hands because it combined dynamics with definition of conjugate variables and Hamiltonian, starting from the Lagrangian. So, the definitions of EL and P are, they pop out from the expression for the variation. So, I had mentioned that there were attempts before Hamilton to formulate such principles of least action. I just mentioned briefly, they are in the notes, but it is interesting to know. The Maupertuis principle of least action was stated by him in 1747, and it was put into respectable mathematical form by Euler and Lagrange. It turns out that that version involves restrictions on the choice of the curve C and on the variations of C. So, it is not as free as we have described it here. There is a principle of Jacobi, which must be around 1848, 47, 48, which tries to eliminate time from this whole discussion and tries to directly characterize this curve as a curve in configuration space without worrying where is it at each time, just the trace of that path. There is something by Gauss called the principle of least constraint in 1829, and there is a Hertz's principle of least curvature in 1894 or so. So, all of these things, I think they are briefly described or mentioned in Sommerfeld's book. I just want to say that it's the Hamilton's principle which we all hang on to, and in the extended form it is very, very very nice statement. Just mention that this Maupertuis principle is described in the Goldstein book on page 356. It is in the Landau-Lifshitz book on page 140. All these things are given in my notes, you don't have to write it down, and it is in the Sommerfeld book. The Jacobi principle is described in Goldstein's book and in Landau and Lifshitz, not in Sommerfeld. Gauss and Hertz principles are described by Sommerfeld, and I think Hertz principle by Goldstein, but Landau and Lifshitz do not refer to the Gauss principle or the Hertz principle. I think it's a reflection of the fact that they are not as flexible and as easy to use in a practical sense as the Hamilton principle.
Was Hamilton aware of the extended Hamilton principle?
Not as far as I know. That came late. Yeah, but I don't know exactly in whose hands, but not in Hamilton's hands. Now, yeah. Yeah.
When one teaches classical mechanics,
Yeah.
one says, but I just want to clarify one thing, that does one, if I look at that expression for the change in the action.
This or that?
No,
This one? Yeah.
So does one say that the quantity within the bracket, that is zero along the solution set, and therefore the action is zero, or does one say that no, this delta q could be arbitrary and therefore the bracketed quantity is zero, and therefore one gets lucky?
Yeah. So you both are valid statements. If you assume that the motion is such that the differential equations are obeyed, then you read this as a property of the action. But if you say, I want to derive or state the equations of motion from a new point of view, you say, the motion shall be such that this action shall be stationary. Then stated in that way, it leads to this as a consequence, the vanishing of this one. It's really up to you, okay? All right. So in Sommerfeld's book, there is some little bit of discussion after this part about the teleological nature of physics. Does it mean that the future determines the past, that kind of thing? As far as I can understand, from the mathematical point of view, the two ways are equivalent. One implies the other, both ways. The differential equations, the action principle stationarity amount to the same thing. This mathematical relationship doesn't say, therefore, nature moves so as to reach a certain desired end at a later time. That kind of thing, it's up to you. You want to say it or don't want to say it. The mathematical relations are not forcing you to make such a statement. Okay? So that's all I want to emphasize. So you please read this part in Sommerfeld's statement. And then there is a very beautiful book by a man called, I don't know how to pronounce it. It is a Hungarian name. You know how to pronounce it?
I don't know how to. I pronounce it as Lanzos.
Lanzos. Yeah. Whether it's Lanchos or. you must start a collaboration with the Hungarian physicists. And then you by Hungarian.
Tamastel.
Oh, I see, okay. So this is he was a contemporary of people like Dirac and so on, and it appears that there were many things he had done. He was trying also to discover quantum mechanics in some sense, but he did not succeed that much, and Dirac and Heisenberg, they overtook him. And so he is from that generation. Maybe he is a little older than Dirac. And in the historical incident, in 1972, there was a conference held in Trieste at ICTP by Abdus Salam to celebrate Dirac's 70th birthday. It's a very famous conference. The proceedings of that conference is an invaluable volume. It is called The Physicist's Understanding of Nature, some such thing, edited by Jagdish Mehra, I think. And it turns out, until 1972, Dirac and Lange-Josse had never met. They have been working on the same problems for so many years, 50 years. And there is a priceless photograph of Lange-Josse at last meeting Dirac in that Trieste conference. Lange-Josse looks very, very old in that picture.
But I think if it's the same Lange-Josse, he will be known to most of the younger people here.
How? Huh? Yeah, so now I was going to say there's a beautiful book by him called The Variational Principles of Mechanics. It is a Dover publication.
But also this method of finding the largest eigenvalue. I mean, is it the same?
Yes,
Okay, so it's a numerically powerful technique.
When was that done by him? Must be after quantum mechanics had been created. Anyway, so the idea of bringing his name is the book. It's Variational Principles of Mechanics, very, very beautifully written. It is a Dover book and it is easily affordable. Okay. So I learnt this version of the action principle, this extended Hamilton principle, from Sudarshan. Not before that, I didn't know. So we used it in our book also. Okay. So now I come to the next topic, and that is the transition from the, I will use this shorthand notation, the Lagrangian form of the equations of motion to the Hamiltonian form of the equations of motion. We have seen already the transition from the Newtonian to the Lagrangian form, and now I go to the next step. I had mentioned this yesterday morning. These are all mathematical developments, newer and newer ways of expressing the same physical content which was already there in the work of Galileo and Newton basically. But the mathematical way in which to present it became more and more sophisticated. And so this is the second stage in this kind of development. The remaining one is to reach the Hamilton-Jacobi equation, but that I will come to later. So as we have just seen, the extended form of the Hamilton action principle is useful in the sense that it leads naturally to these expressions, something called canonical momentum variables, something which will later be called Hamiltonian, the Hamiltonian. Here it is just the Legendre transform of the Lagrangian. At this stage, okay. Now, in all non-relativistic systems, the Lagrangian obeys a very interesting, very useful condition. This second derivatives of the Lagrangian with respect to the generalized velocities is a real symmetric matrix of dimension n, n being the number of degrees of freedom. So, it is usually the case in all non-relativistic situations that this determinant of the second derivatives, partial derivatives, as a matrix is non-singular. It has an inverse. Then in general, if this is true, we say that the Lagrangian is a regular Lagrangian. Regular means in this context, this matrix is non-singular. It has an inverse. And as I said, in non-relativistic situations, the kinetic energy is quadratic in velocity, is positive definite. So, this condition is usually obeyed. But in other cases, it may not be obeyed, extending when you go away from non-relativistic situations. So, if the Lagrangian has this regular property, I must say, why is this word introduced? This was brought in by Dirac in his work on constraint mechanics, which I described a year ago here. If the Lagrangian does not obey this condition, all kinds of unexpected things happen. As a definition, a Lagrangian, if it is not regular, if this determinant is 0, that means this matrix does not have an inverse, we say the Lagrangian is singular. And Dirac did a beautiful piece of work, relatively late in his life, you can say, showing how to handle a singular Lagrangian and how to go to a Hamiltonian form for such a Lagrangian. I will not be doing this at the moment. It is there in the notes towards the end. Now, if the Lagrangian does have this nice property, which, as I repeat, it usually does in non-relativistic cases, it implies several useful things. These equations for momentum as partial derivatives of Lagrangian with respect to velocities can be I will say inverted for q dot in terms of q's and p. You take this set of equations, the Lagrangian is a function of q and q dot. So, every p is a function of q and q dot. You can ask the question, can I, in an algebraic sense, turn these equations inside out and express every q dot as a function of p, and q, of course, is always there. That can be done if this condition is satisfied. Okay? This is called a, well, it's a so-called implicit function theorem. And it also amounts to the following statement. From the Lagrangian equations of motion, we can find the accelerations q double dot. Okay. When you write the Lagrangian equations of motion, here it is. It just says this thing is 0 for each degree of freedom. It is not obviously clear from this expression that you will be able to extract q double dots. I mean, it's not evident. It's not, doesn't strike you in the face. You don't immediately see it. If the Lagrangian has this nice property, it is guaranteed that from the Lagrangian equations of motion, we will be able to express every generalized acceleration as a function of q and q dot. Every q double dot is expressible in terms of q and q dot. So, these things are all true. Okay. So, what happens is that if in the Dirac sense the Lagrangian is singular, then this thing fails. You may define canonical momentum in this way, but you are not able to invert these equations. You are not able to express every q dot in terms of q and p. That fails. And at the level of the equations of motion, if this is not singular, you are unable to find all the accelerations. So, such Lagrangians, they are not pathological, they are there in so called gauge type theories. Any theory Lagrangian which has a certain extremely large amount of invariance, continuous gauge type invariance, inevitably this determinant has to be 0, it has to be singular. So, it is not a curiosity, but a very important case, and that is why Dirac constructed his theory of constraint systems. Okay. So, now I will just jump a little bit and write equations which you are all very, very familiar with. They are the following. I will assume this is a non-zero determinant. So, this matrix has an inverse. So, it follows that, as I have written here, every q dot can be written as a function of q's and p's from this set of equations. So, these are initially to be thought of as definition of canonical momentum. Then we write them down and turn them inside out, solve for every q dot on the right in terms of p. Q is always there. So, that can be done in a way which you are familiar with, which I will show, and there is also this Legendre transform of the Lagrangian. So, the things that I will write now are very well known to you. This quantity EL, the Legendre transform of the Lagrangian, it is an expression in terms of q and q dot. Since it is true that I can regard q dot as a function of p, I can imagine rewriting this Legendre transform not as a function of q and q dot, but as a function of q and p. When I do that, I give it a different symbol and I call it the Hamiltonian. So, by definition, the Hamiltonian is a function of q's and p's by definition. It is not a function of q and q dot. Okay? So, you must keep that clearly in mind. And the fact that you can solve for q dot formally, here is that solution. This is also something you are very familiar with. Okay? So, these two things I have written here, one, they make this solution, the inversion of this system of equations, in some sense explicit by saying, first go to the Legendre transform of the Lagrangian, write it as a function of q and p, give it a new symbol and a new name, H Hamiltonian, and then the solution for q dot in terms of q and p is given here. So, all the steps leading to this are very familiar to you, and I will not go through them. Then the last question is, so this is half of the transition from Lagrangian description to Hamiltonian description. The last step is, what about the equations of motion themselves? That is very easy. I will write it down and then you will recognize it. What is the Lagrangian equation of motion? It says this thing is to be 0. So, what is this? Delta L by delta Q minus d by dt of p. So, the equation of motion is a statement dp by dt equals this thing. This can be easily shown to be minus delta Hamiltonian over q, delta q. All right. So, this is the Hamiltonian version of the equations of motion. They are called the Hamiltonian or phase space equations of motion. Okay. So let me just express it in this way. When the Lagrangian equations of motion are written in Lagrangian form, we know that again for non-relativistic systems, basically it's a system of second order ordinary differential equations in time. But in some way you can say the Q double dot are buried inside this Euler Lagrange equations. The equations, when you look at them, they don't say Q double dot equals such and such. They don't say that. It's buried inside. Once you go to the Hamiltonian version, the spirit of the treatment is you now imagine Q and P being treated as variables on the same footing. And the equations of motion are first order ordinary differential equations, and they explicitly say, so my variables are Q and P, here is the expression for Q dot, here is the expression for P dot. They are first order equations, and the equations as ordinary differential equations are explicitly given. So that is a qualitative difference between the Hamiltonian approach and the Lagrangian approach. Okay. There is a way to rewrite Hamilton's principle in the phase space form. I will not do that here. It is there in the notes if you are interested. Now there is a very nice advantage in writing the equations of motion in the Hamiltonian form, and that is the following. Since they directly tell you dq by dt is such and such, dp by dt is such and such, if you were to take any function of q's and p, you can immediately write down an equation of motion for it. Now, this is not something that is very natural in the Lagrangian description. Suppose you started with a function of q and q dot. What is its equation of motion? It can be worked out, but it is not a very natural operation. In the Hamiltonian form, it is much more explicit, and you can see as I write, this comes out very easily. Why? The total time derivative of any function of q's and p's is partial with respect to q times q dot plus partial with respect to p times p dot, and there is this minus sign. Okay. So this is a virtue of the Hamiltonian description of dynamics, in that it leads to a simple and natural general equation of motion for any physical quantity. Okay. Maybe I am stressing this a little too much, but it is really for the benefit of those who may not have seen these things earlier. But that subset here must be very small. Those for whom this is new, I think this is well known to all of you. Okay. All right. So this expression, so now I rub out some of these things. So this expression on the right hand side leads to a very important definition. It is called the Poisson bracket. If you take any function of q and p, f, and any other function g of q, p, the thing that appears on the right hand side in that general equation of motion motivates us to define the expression I am writing down. It is called the Poisson bracket of the function f with the function g. So among functions of q's and p's, there is this very interesting operation. Given any f and g, both of them functions of q and p, we are able to construct a third function of q and p. So if you like, I will write it as h of q and p. All right. So it is called the Poisson bracket of f and g. This is a very important construct in Hamiltonian mechanics. So I have gone pretty fast and pretty far because I was able to omit many derivations. Also because I exploited yesterday's tutorial session to some extent. So this is where I wish to stop here, and I will pick up tomorrow from the properties of Poisson brackets and what are the things you can do with them. But I will give now, I will stop well before 11, so you can send the signal for the coffee and tea to start getting them ready. I will give one simple example, and then I will just mention a preview of coming attractions. Right? So maybe I mention the latter first. The Lagrangian form of equations of motion, it has a natural covariance group. What does it mean? There are natural changes of variables which preserve the structure of Lagrange's equations. It doesn't mean that the Lagrangian is preserved, but you start with a Lagrangian, write down its equations of motion, you make a certain transformation, then there is a way to write a new Lagrangian in terms of which the equations of motion look exactly as before, structurally. Those transformations are called point transformations. They are changes of q to q prime. All right. Now, and they more precisely, I mean, physicists use a somewhat sloppy way of dealing with these things. Point transformation should be thought of really as mappings of configuration space onto itself. Take a point q in configuration space, a point transformation maps it to some other q prime. So q prime is to be a function of q in such a way that it can go backwards. This is the idea of point transformations, and Lagrange's formulation of mechanics preserves its overall structure under such transformations. Now when you come to the Hamiltonian, of course, because it states the same physical content as the Lagrangian, it will also be preserved, it will preserve its form under point transformations, but it has much larger covariance group. There are many, many more transformations of variables under which the Hamiltonian description is preserved, and those are called canonical transformations, and that is what I will describe tomorrow. So what happens is, you can say the space in which Hamilton's equations are to be viewed is not configuration space, but something called phase space. And a point in phase space is labeled not just by q alone, but q and p as independent variables. So immediately you can see that for a given configuration space, the phase space is twice the original dimension. If there are n-dimensional configuration space, its phase space is 2n dimensional. So the use of the word phase space by Shamik yesterday evening has to be taken as a slight generalization of the older terminology. In the older way of doing things, every phase space necessarily is even dimensional. There cannot be a 3-dimensional phase space in the older definitions, because it is twice the dimension of the configuration space. So there is a 2-dimensional phase space, 4, 6 and so on, nothing like a 3 or 5-dimensional phase space in the traditional way of doing things. So the transformations which preserve the structure of Hamilton's equations are mappings of the phase space onto itself, and they are an immeasurably larger set of transformations than the old point transformations. So here, so I will write it here, these point transformations, they describe the invariance, covariance property of Lagrange's equations, and here we have canonical transformations, often abbreviated by CT. And Shamik was asking, when will I describe them? I will be doing it tomorrow, not today. Okay? But what I want you to appreciate is that this is a certain family of transformations. This is unimaginably larger than that. Every point transformation is a canonical transformation. That is a part of this. It's a subgroup, we say. But canonical transformations as a family form a much, much larger set of transformations. And these are very important in the development of classical mechanics, in the whole of what is it called, perturbation theory, in the hands of people like Poincaré and all these people. Who are the others in the some French, other French mathematicians, Delaunay. All these people who worked in celestial mechanics problems, they used the Hamiltonian form of mechanics, and the machinery of canonical transformations was used in classical perturbation theory. When quantum mechanics came, the idea of canonical transformation was replaced by unitary transformation. So that is why the Hamiltonian form is very important one to understand well, because for these things, canonical transformations, there is an analog in quantum mechanics. Point transformations can be regarded as trivial. It is like, instead of, well, this is a loose statement. The transition from xyz to r theta phi is sometimes called a point transformation, a change in coordinates. It's not a good way of describing it, because the change from xyz to r theta phi is not naturally interpreted as a mapping of configuration space onto itself. It's not true. A three-dimensional rotation is a point transformation. xyz going to rotated x prime, y prime, z prime is a point transformation. But at least in the older books, physicists were somewhat loose or lax in this respect. The word point transformation, the concept was used, but used with certain lack of rigor. Okay. So one of the things we will describe, I'll start tomorrow, is the description of the phase space version of the equations of motion, the notion of canonical transformations, and so on. And I will just end with one simple example. Let us see, where shall I write it? Yeah? In volume element where? In phase space. No, in no, there is no such property at all. No such property. No. Okay. Yeah. So you make one mapping. Let's talk of Lagrangian situation. A point transformation, more strictly defined, is a invertible mapping of configuration space onto itself. So it will take a point with coordinates q to some q prime. Then you make another point transformation. It will take q prime to some q double prime. The product transformation takes you directly from q to q double prime. That's all. So the composition of point transformation, it's just like composition of mappings. Okay. So that is very straightforward.
Phase space is a two-dimensional matrix.
Yeah. So
that's why it's a bigger space.
yeah, but see, this is quite a delicate point. You can imagine apart from being careful in certain ways, that any mapping of configuration space onto itself is an allowed point transformation. Any mapping of capital Q into capital Q is allowed. It will preserve the structure of Lagrange's equations of motion. When you go to phase space, it is not true that any mapping of phase space onto itself will preserve Hamilton's equations of motion. If you have a mapping given phase space onto itself and you ask, will it preserve Hamilton's equations of motion? Invariably the answer will be no. There are very special kinds of transformations of phase space onto itself which have the property that they will preserve Hamilton's equations of motion, in the sense that they will allow you to define a new Hamiltonian. So those are what are called canonical transformations. So in that respect, point transformations, very mild conditions. They just have to be invertible and smooth in suitable sense. Canonical transformations, they have to obey some requirements. If a transformation on phase space doesn't obey the conditions which we will see tomorrow, it will not be allowed, it will not be a canonical transformation, it will not preserve Hamilton's equations of motion. So one other thing I wanted to say is that I mentioned it, I think, briefly yesterday. Mathematicians sometimes say, see, after all, this phase space concept came in the work of Hamilton. And in modern mathematical way of doing things, given any configuration space, there is a very nice way of immediately constructing a corresponding phase space. It's a purely differential geometric approach. It does not require that you should have a Lagrangian in mind. Okay? So the passage from configuration space Q to its corresponding phase space, which is double the dimension, is done in a very, I can say, slick way in modern mathematical treatment. In Hamilton's time, it was not done in that way. It was in the language of mechanics. You went through the Lagrangian to define canonical momentum, but now it does not have to be done in that way. But mathematicians nowadays say probably Hamilton's greatest discovery was the idea of a phase space associated with every configuration space, a manifold of double the dimension with all the properties that it carries, the Poisson bracket concept, the conditions which define a canonical transformation, so on and so forth. Okay, so I think I will stop. I said I will stop before 11. I will skip this example, but since everyone now has my notes, you can look at equations 55, 56. A very simple toy example of a Lagrangian, how to go to its Hamiltonian. Okay, I leave this as an exercise. Fine, so we stop at this point. Okay.